Hello everyone. Let us start discussing about what was happened in seventh week of this Calva theory course. We'll solve some sample questions. Okay. So if you have doubt, because many of you are not here, you might be looking in YouTube channel. So comment the questions if you have regarding this session. Okay. Okay. So let me start. I hope my screen is recorded now. Okay, so this is a summary about uh, the results we discussed in this week and in last week. So this is about finite Galois extensions, L over K, a field extension, finite field extension, and this group, which is automorphisms of L, which is K algebra automorphisms of L, okay, that is called Galois group of this extension L over K, and denoted as Gal L over K. Then, using this definition, we had defined that what are Galois extensions. Okay, what are Galois extensions? A Dedekind-Artin result shows that Galois group of this extension L over K is less than degree of extension L over K. Okay, when they are equal, we say it is Galois extension. Okay, its equality holds in the here. Okay, okay. So this is a result which is used to define Galois extensions. And then we have action of Galois group. L over K be a field extension. We have also proved Galois correspondence in this way. So Galois group naturally acts to L because is it just the algebra to becomes of L. So it in fact acts on L. Sigma gamma x goes to sigma of L. Okay. Okay. So the following statements are also proved in the lecture. Look into it. L over K field extension. If some element of kx polynomial with coefficients in k, then Galois group of L over K operates naturally on VLF, means something, some element of L which is 0 of F, then sigma of that 0 will also be 0 of F. So that is why VLF is fixed subset. That is the action of Galois group restricts, okay, to VLF. So this is also natural. Sigma comma x goes to sigma of x. And next is 0 of f. Sigma of x is also 0 of f. That is what it restriction means. L over K is finite Galois extension. Then its uh, its subfield to this Galois group is just K. Okay, this is also done in the class. So okay, remember these things. When a simple extension is Galois extension, then that minimal polynomial for x is separable, and all roots are distinct. And inside kx, this irreducible polynomial has all its roots. Okay. This would belongs to kx of x. It's L is k, that is all the roots should be inside L, and L should be simple extension. Okay, so Galois group also operates transitively on zeros of it. Means the action of the group GLK GL Gal of KX over K into this set action is transitive. Okay, that is if any x1 uh, act its orbit will be whole of this set. Okay, that is this subset, this zero set has only single orbit. That is what action transitive means. Okay, okay, so finite Galois extension L over K is simple. There exists primitive element F. Okay. Finite Galois extensions are simple. This is also proved in the class. Okay, so right now I'm not going to discuss this. Assume this summary of results as it was done in the class. So here I will solve some sample questions which is given to us. Prove or disprove L over T is a finite field extension. Then L is equal to C. L over C means L is any with bigger field than C. Okay, this is right. We want to show, can we show this C contains L? Question is here. If they are, if the both are true, means L is subset of C and C is subset of L, then C will be equal to L. Okay. So how to do this? We are given L over C is finite extension. Let X belong to L. So then also we are given uh, and because this extension is finite, L over C, so we can write L over C is equal to N. There is some technical issue here. Um, this is just written L over C is equal to N. Okay. And what about this set? X, 1, x square, and so on. X power N. How many elements are these? This collection is cardinality of this set is N plus 1. So it is dependent set, right? Dependent set of vectors in L over K. Because degree of extension is N, that means L as a vector space over C has dimension N. Right? This set has N plus 1 element. So it should be linearly dependent. Linearly. So there exists AI in K, not all zero, such that summation AI x x power I from 0 to 10 is equal to 0. Okay. So this implies x satisfies some polynomial. X satisfies some polynomial in Kx. This implies X is algebraic over here, right? It was random element, X was random element, so every element of L is algebraic over K. But if we show that C is algebraically closed, if we assume that C is algebraically closed, then this will imply what is K here? Sorry, L means yeah, L as it is, K is C. Okay. X is algebraic over C. If C is algebraically closed, then X belongs to C, and we are done. Okay. This is what we wanted to show. Any element of L is also element of C, hence any subset of C. Okay, good. Now, from here it is not clear. This question is all about uh, saying all about C is algebraically closed. Okay, so better we should prove that C is algebraically closed using Galois theory, or you might already be familiar with this in analysis or complex analysis. We have seen that C is algebraically closed. Okay, in algebraic closed means any polynomial which is represents from C, or any polynomial in CX, element of CX, has all its roots inside C. Okay, so it is splits completely inside C. Okay, so we would like to see if there is a proof that C is algebraically closed using Galois theory. Can we see that? How to see this? Okay, so how will we see? Let me write here. Our claim is that C is algebraically closed. So again, we'll take some algebraic extension L over C, and we'll see that L should be C only. Let finite algebraic. So give any polynomial will give us finite extension, which will be algebraic Cx mod f given like this. So we'll better take finite hence algebraic extension. So as, as is given in our case, so we'll take let L contain C be finite hence algebraic. We have shown above. So finite hence algebraic extension. Now we'll show that L is equal to C. Yeah, that will show that L is algebraically closed. Any element which is algebraic, every element of L is algebraic over T. This is given, and we will show that L is equal to 0. Okay, how to see this? So we know that C over R, this is algebraic extension, right? 2-degree extension or is algebraic extension. So any element of L will take this. This should be noted. Let X belongs to L. Okay, because L is finite algebraic extension, L can be L is of the form Cx mod fx. What look some effects. Finite algebraic means this kind of extension because L is field. This yeah, that should be reducible. Yes, is reducible has maximal. So inside C, F should be only 1 degree polynomial. That is what we want to show, right? Then only L will be equal to C, and this will be equal to C only. So we have to show irreducibles inside C. Yeah. Inside C, yes, they are 1 degree polynomials. Okay, anyway, uh, coming to this, let X belongs to L, then X is algebraic over C, hence algebraic over R, right? Because C over R, this is also algebraic extension. So this is property of algebraic elements. I think this was discussed in third week. Okay. Anyway, now, so what about splitting field of mu x r? Okay. Let mu x r be irreducible monic polynomial uh, minimal, which is minimal polynomial of x over r. Then by Kroneker's theorem, existence of a splitting field, then there exists a field and there exists a field L which contains C, hence contains R also, such that that is a splitting field of mu x. Mu x, let me take a splitting field only, not arbitrary extension. L is a splitting field of mu x. Okay, so oh, we are writing again L. So this is problematic. We should write something else. Let me write L prime or okay. Let me write this one L prime. Uh, the next one as L only. So this is splitting field of USR which contains C also. Splitting field of mu x. Okay. Okay. So this extension we have L over C, C over R. Okay, so let this is Galois extension. Okay. We can find that L is splitting field of mu x R, and this is also separable because characteristic zero. A, any irreducible polynomials they are separable. So it becomes Galois extension of R. Okay. R L over R. This is Galois extension. Galois and L over R is Galois extension. Okay, so let C be Galois group. This is 2-degree extension, right? G be Galois group of L over A or L over R or Gal. Then two because what will be the order of G? Order of G is same as order of this extension. Right. That is how Galois extensions will be defined. Degree of L over R. But degree of L over R, this can be factored as degree of C, sorry, L over C, and then uh, C over R. But C over R is just 2-degree extension, okay? Because C is nothing but uh, R x modulo x square plus 1. So this is 2 times L over C. This implies 2 divides order of G. Okay. Now, so do you understand what I'm going to show? I will show that L is equal to C, that is mu x R, it fits completely inside C. So in particular, what where X will be? X will be inside C. Okay. Okay, we'll come to that. So 2 divides. Now this is from group theory. Consider 2 silo subgroup of G. Say it is H. Okay. Then this index G mod H. This is odd, right? Order of G mod H is odd because all the powers of 2 have been cancelled with order of H. So order of G mod S is now odd. What about this extension? So we'll use Galois correspondence here. Then let M be L, which is fixed field by H. Okay, this is also denoted as fixed H L. Elements of L which are fixed by elements of H. Such that sigma of X is equal to X for every sigma belonging to H. Okay. H is subgroup of D, which is automorphisms of L. Anyway, this is also a subfield, which has been shown in first video of this lecture, first lecture of this week. This is a field, intermediary field entire. So here we have L, M, R, and this side we have what fixes L, only identity fixes L, what fixes M, H, what fixes real numbers, it is G. Okay, G is just fixed, sorry, not here. R is nothing but fixed G, L. Okay, so whole G fixes only R. Only identity subgroup fixes whole L. Okay, this is identity map of L, identity automorphism of L. Okay, anyway, uh, this is in Galois correspondence. This is other side. This is inclusion reversing, right? So what is degree of X? This is Galois correspondence. This M over R, which is also M is nothing but LH over R. Elements which are fixed by H. This is the notation. I'm just using that. What will be this degree of extension? This is nothing but uh, index of it, G mod H, also noted as G colon H. Okay, this is odd. This is odd. Okay. Now we will show that M is equal to R and H is equal to G. Hence, H is equal to G. What we will use is that every odd degree real polynomial has a real solution. Okay. So this extension is odd degree extension. This is odd. Then we'll show R is equal to M. How? Uh, let Y belongs to M. Then what is degree of extension? Degree of extension of KY R. Ry over R is divides degree of extension M over R, right? This is just from degree formula. Degree formula. You just check it. That in this case, M R Y R. So this extension, the bigger extension is multiple of this individual extension. Degree of individual extensions. Okay. So that is why R Y over R, this extension divides degree of this extension divides degree of bigger extension. Okay. That is what is written here. Okay. I hope you understood this. Then this implies Ry, let me write like this. I can write round bracket or big bracket as square bracket as required because y is algebraic anyway. So both are same. So this is also odd. This is also odd because odd numbers only divide odd. When Ry is odd, this implies this is now simple extension. You see, this is simple extension. Note this is simple extension. And this degree is odd. This implies what? Uh, Ry is same as Rx modulo mu y. Uh, this is minimal polynomial of y over R. So this degree is if degree of extension is odd. This implies that degree of mu y R, this is odd. So this implies that so from here, because this is field, it should be irreducible and as well as okay. Odd means if and only mu y R has a real solution. This is from real analysis. I hope you know this. When we have odd degree polynomial, we'll use intermediate value theorem and we'll get a real root. Okay, it has a real root. So okay, this is not implication. Okay, this is to understand. Note it. Uh, but also, but mu x, sorry, mu y r is irreducible. Minimal polynomial is irreducible and it has real root also. All this implies mu y r is 1 degree polynomial x minus lambda. Okay, for some lambda inside r. But this will imply y is equal to lambda, hence belongs to r. Now, what we have shown here is that y belongs to M and we have shown y belongs to R. So, we have shown M is contained in R. M was already bigger. See here, this implies M is equal to R. R is fixed field of G. R is fixed by G and G, right? And M is what? Fixed field by H, LH. Means elements of L which are fixed by H, and this is R is elements of L which are fixed by whole G. So Galois correspondence implies from here Galois correspondence implies that H is equal to G. So this discussion shows uh, order of G is equal to order of X is equal to 2 power n, because since H was kilo, that's kilo 2 sub 2. So it H was already 2 power order subgroup. Okay, so for n, for some n. So now we have shown H is equal to G, so that order of G is 2 power n. Now here we have this extension L over C over R, and this degree of extension, which was degree of extension was also order of G, right? Which is now 2 power n, and this is anyway 2, so this is also some 2 power R. But exactly it could be 2 power n minus 1. We will show V1 will show this degree of extension L over C is 1, hence L is equal to C. This will imply, because L is nothing but R attached with Y, right? L was what? No, no. L was a splitting field of mu Y. No, no. We have chosen X in L prime here, and we have, so we are taking L to be splitting field of mu X R. So this becomes Galois extension also. Okay. So in fact, X belongs to L. This implies X belongs to C. So we have started with, let me change the color here. We started with X inside L prime. Finally, we are coming to X inside C. This will imply L prime is equal to C. Okay. So better we should show this degree of extension L over C. This is just 1. If it is not 1, it will be some 2 power. That is clear from here. We'll come to that. If L over C, this is not 1, then L over C will be some 2 power R or some R greater than or equal to 1. Now we'll choose minimal extension. Okay. We'll use again a fact that every element in C and in R, they have square root. Okay. So this implies that Gal Galois group of L over C, which is subgroup of Galois group of L over R, this has order. This is equal to, let's say, This we are already taking G. Let me take it as H I J. Okay, this at J. Then order of G we already know 2 power something. J is subgroup, so that order of J divides order of G. That is why we are getting this extension. This is also Galois extension anyway. Uh, This extension 2 power something. This extension 2 power something. If it is not 1, then we are considering the case. Then take 2 power r minus 1 order subgroup of J. Note that order of J is 2 power r. We are considering such 2 power order subgroup of J, say J prime. Then I'm just writing, it is not required. Its index is 2. And J prime is normal subgroup because its index is 2 inside J. Okay? It is normal inside J. That is also important to say. These are all not required, but correspondingly, Galois extension what will be? For this extension, we will have, okay, let me write Galois extension here. Here we have L, here we have C, and R here. And we are just caring about L over C, so let me delete the lower part. So for L, we just have identity element which fixes L. For C, we have J, which fixes C, and we are considering J prime here, and this index is 2. Right? So here we have 2-degree extension, which is Lj prime. This extension is 2-degree. Because this index is 2. Okay, this is Galois correspondence here, but what we need to show is that J prime is equal to J. It will be the case J prime is equal to J, that will be contradiction because we have index 2. Why is J prime is equal to L J prime? This is 2-degree extension of C. It will look like C root lambda or some lambda. All 2-degree extensions look like this. F root alpha. Okay. This is, you have to note it, or some lambda inside C. But because every element inside C has root inside C, this becomes C. And this is also C is also Lj. Right? Fixed by all elements of J. That is C. Elements of L which are fixed by J, they are C. But this Galois correspondence implies J prime is equal to J. This is contradiction. Contradiction to what? This fact. So what we have to shown that there is no such 2 power r. If there is 2 power r extension, we will get some index 2 subgroup. And index 2 here what we use is that index two subgroups corresponds to 2-degree extensions. Of the here in this case, in any case, 2-degree extension. Then the fact that the fact that any 2-degree extension of f any field is of the form f root alpha or some alpha which is not a square inside f. For example, if we have, but this is not the case for C. So for C they are equal. C root alpha and C they are equal. Okay, this is explanation for blue star. Why this is equal. Okay, so I hope you understood this. After all, we have shown that this extension is 1 degree and hence L is equal to C. And inside X was belonging to, initially we took X in L prime. Let me write in last line so that it will be clear. We started with X inside L prime, which was bigger than C, which is finite algebraic extension. Then we considered containing C splitting field of mu x r. So which the step was X belonging to L. L again contains C and C contains R, and these extensions are Galois extensions. Now these are Galois extensions. Galois. We consider such, and this from here we have shown that L is equal to C, which implies X belongs to C, and from this arrow we have shown X start. All this together implies L prime is equal to C. Okay, so this was first question. Okay, so it took 50 minutes to explain. This was important. It might be discussed in the class. Yes, as an application of Galois theory. This was important. Okay, so for any prime p, this extension is Galois. Fpx or Fp. Okay, okay, for b, Fpx over Fp is for p. I will just say that it is not. It's not well. You can just look at uh, because this is primitive element x, but its minimal polynomial not Galois. Why? Mu x and this field, let me denote it by k by L. L over k, this section L. Mu x k, this is this polynomial mu x k of t, variable is t. This is t power p minus x power p. This is minimal polynomial. I'm just writing the logic behind why it is not Galois. But wherever they split mu x t, mu x k, this polynomial is not separable. You can just take derivative and it will become 0. because this is constant or whatever. P will come outside. Yeah, this is constant over because this belongs to K. So this is anyway 0 and this will be P power P minus 1. But P is 0 because we are in FP. So that is why this is not separable. In fact, I'm just writing what is factorization of this. P power P minus X power P. This is uh, P minus X whole power P in L. So this is not Galois. The most third part. K root Q root 2 K root 3. We have to find basis Q algebra K, K algebra L, Q algebra L, and minimal polynomial of roots of this root 3. Is the field extension Galois extension? We have to check all these things. We'll solve it. Okay. Part C. We have here Q root 2 root 3 Q root 2 and Q. This is also denoted as K and this as L. Right? Yeah. If that's the notation. Yeah. This is the notation. L is K root 3. That is the same thing. What is written there. This can also be written as K root 3. K attached to root. Okay. So we have to check what is basis of K root 2. Sorry, K over Q. K over N. Q. This is K is vector space over Q. And what's the basis? How will you find basis? K is nothing but Q x modulo x square minus 2, right? From here, what should be your basis? 1 and x. X square will be minus 2. So only 1 and x are basis. But x is root of this polynomial x square minus 2. So how to write this? In fact, 1 or root 2. This is basis of K over 2, okay? And what is degree of extension hence? 2. What about L over K? What should be the basis? 1 root 2, everything is inside K only, so they are constant. We are missing just root 3, right? We have to see if root 3 also belongs to K. If it belongs to K, then L is equal to K. In fact, yeah, we have to see. Uh, we just claim here root 3 does not belongs to K. This implies L is nothing but K x modulo x square minus 3. Okay, so here 1 and x This this is your basis. It is nothing but x, sorry, 1 and root 3. This is your basis. This claim is proved here. Okay. Let me prove here. If root 3 belongs to K, what will happen? Yeah. If root 3 belongs to K, root 3 can be written as uh, A plus B root 2. And then if we, where AB belongs to Q, let us square first. This side we will get 3. Here we'll get A square plus 2B square plus 2 root 2 AB. Okay. But from here, what you can conclude, this is irrational and this part is rational. You can subtract from going other side. But anyway, this particularly implies 2 root 2 AB. This should be 0. We can just use that 1 and root 2. They are basis elements, right? And 3 minus A square minus 2B square. This is also 0. So here root 2 root is implied A equal to 0 or B is equal to 0. But A is equal to 0 will imply B is equal to B square. Okay, let me write here. A is equal to 0 implies B is equal to 2B square. Here is a contradiction. Is there any contradiction here? B has no denominator multiple of 2, otherwise B it can have. Yeah, B is equal to 2B square, and this implies in particular that 3 divides B. Yeah, but where? Inside integers or inside Q? Okay, so here what I was discussing is that 3 is equal to 2b square. This implies that root 3 by 2, which is equal to b, hence belongs to q. This is contradiction. We have to solve. Okay. And if b is equal to 0, then 3 is equal to a square, which implies that root 3 belongs to q. Again, a contradiction. Okay. So what we get that root 3 does not belongs to q. This is the discussion for that. So root, this extension, both are 2-degree extension. In particular, yeah. So here we understood that 3 does not belongs to k. Root 3 does not belongs to k. So this is 2-degree extension. Yeah, this was anyway 2-degree extension because root 3 does not belong to k. This is also 2-degree extension. The total extension is of degree 4. And we'll see this L is L, which is q root 2 root 3 is same as q root 2 plus root 3. If we show this, that this L is simple extension over q, then we'll get the, more thing we have to calculate, right? What is basis of L over q? If you remember the degree extension formula, when we consider basis of k over q, basis of L over k, how to get basis of L over q? We'll just multiply xi by j, right? So here we have 1 and root 2, multiply with 1, there will be 1 and root 2 only, multiply with root 3, what you will get? Root 3, root 6. This is root 2 into root 3. So this is your basis for L over Q. So this is 4-degree extension. Okay, good. So we'll show that this is simple extension. That this is primitive element for that. Okay. So one side is clear, right? L contains U root 2 plus root 3. This is easy. Yeah, this is too much very clear. Now we will show that root 2 belongs to, okay, we want to show we want to show L is also contained in Q root 2 plus root 3. Then they will be equal. How will we show this? If we just show that root 2 belongs to Q root 2 plus root 3, then root 3 also belongs here. And in particular, L will belong. Means L will be subset of what we want to show will be clear, right? Just root 2 belongs to here is enough. Enough to show. Because once root 2 is there, root 2 plus root 3 is already there. So subtract one from other, you will get root 3 also. And q is already here, so q root 2 root 3 is also subset of q root 2 plus root 3. So this is enough to show this much. How will we show this? Yeah, how to show this? We'll show for P and Q general thing, okay? In the next exercise. The next exercise. That is 7.2. Okay, we'll do this in the next question. This question is clear, right? Yeah. Is the field Galois extension? This question is answer is yes. We'll see in the next exercise. Okay. Let's go to 7.2. Here we have similar question. L is suppose PQ, P and Q are distinct primes. So 2 and 3 are in particular. Is L over Q simple extension? We will show that this is same as Q root 3 root Q. This is as we have shown for, okay, not yet shown. We'll show this. It is simple extension. If answer is yes, yes. And the primitive element will be this P plus. Compute the Galois group and list all intermediary subfields. Okay, we'll do this. When exactly the field L over Q is Galois extension. Okay, let's see. If L is this, it is always Galois. First part, A part, enough to show, as both the case in there, enough to show root P belongs to Q root P plus root Q. Then Q root P root Q. This will be same as Q root P plus root Q. Okay, how to show this? We'll get into it step by step. We have P root P. So root P plus root Q to the whole square. This becomes P plus Q plus 2 root P into root Q, right? Okay. This element already belongs here. We have to disappear this root Q, then root P will be in terms of elements of Q and this term. Okay, good. You can write uh, root P plus root Q whole square minus P minus Q divided by 2. Here we have root P into root Q we can just multiply by p plus root q again. Then what this will be p root p plus root q. Here also we'll multiply that um, root p plus root q. This becomes p root q plus q root p. Okay. Okay. In place of p plus root p, let me write x is equal to root p plus root q, so that this becomes easy to write. X into x square minus p minus q by 2 is equal to, if we subtract now, if we subtract both sides by p into x, which is root p plus root q, then this side becomes p p root q. Oh, why I'm writing bracket? P root q plus q root p minus p root p minus p root q. So this cancels with p root q. Now whatever is left is this q minus p root p here. So we'll go next slide. All this implies, this is again, this is x only. Okay. Let, let me delete it. I'm not writing in denominator, so that should be clear. So root p is equal to what we have seen. P minus q is anyway non-zero. P and q are distinct prime of relatively co-prime. So this is x, x square minus p minus q divided by 2 minus p, that's this total thing, and divided by q minus p from here. This will go the other side, the denominator. But if you see this sub part, other than x, everything is inside q. So this belongs to q, qx. But x is nothing but this p plus root p plus root q. This is q root p plus root q. So we have shown it, right? Now once root p belongs here, root q also belongs here. So hence q root p root q, so both belongs here. Hence whatever we wanted to show is clear. This part is done. They are equal. This extension is simple extension. Answer is yes. Find primitive element. This is your primitive element. Compute the Galois group L over Q and list all intermediary field. This we have to show. Part B. Galois group of L over. So what is yeah? What is degree of extension? U root P plus root Q over Q. This is 4 degrees. Right? We'll do the case. Okay. In fact, let me write like this diagram for it. Q root P here, Q root Q here, q root p q. Okay, this is over q. These are all over q, and here we have L, which is q root p plus root q. This is a diagram for fields. What will be corresponding diagram for Galois group? G fixes q, so G will be here. What fixes? Okay, let me write first G what it is. We have four elements. One, which is sigma 1, sigma 2, sigma 3, sigma 4. Because this is 4-degree extension, we will have Galois group of order 4. This is Galois extension. That is why we were having Galois extension degree and Galois group. Okay, so here we have just sigma 1, which is 1, identity of L. So we will have three subgroups, H1, H2, H3. What corresponds to that? What is sigma 1? We know this is identity. What sigma 2? So here we have root p plus root q. It will be minimal polynomial, which is irreducible monic minimal polynomial for root p plus root q. It will be of degree 4. All its root will be, okay, let me write first root and then v of mu root p plus q over q. This polynomial is just having four roots, plus minus root p plus minus root q. Okay, hence there is no comma here. These are collection of four elements, like 1 1 1 minus 1 minus 1 1 minus 1 minus 1, kind of these four elements. Okay, identity fixes all these four roots, so that is your sigma 1, sigma 2. Sigma 2 is defined by, these are all primitive elements. Okay, so in fact same thing can be written as, that is q root p plus root q. This is also same as q root p minus root q, or you can change plus minus anywhere like this. Okay, these are primitive elements of the extension. So how sigma is defined? We have noted here what is G. G are or automorphisms of L. What is sigma 1? Sigma 1 is identity of L. How sigma 2 is defined? We have to, if we define on primitive element, then other elements are corresponding, because these are algebra homomorphisms. We know everything. So for primitive elements, you have four roots. Let me write it here. X1 is equal to root p plus root q. X2 is equal to root p minus root q here. X3 is equal to minus root p plus root q. X4 is equal to minus root p minus root q. So sigma 2 we can define as on, we'll just say where x1 goes, because x1 decides automorphism. X1 is primitive element. So sigma 2 of x1 goes to We have four choices. If sigma 2 of x1 was x1, it was identity. Sigma 2 of x1, we will define x2. Sigma 3, how sigma 3 is defined, we will send x1 to x3. How sigma 4 is defined, we will send x1 to x4. So in particularly, if you see what sigma 2 is doing, sigma 2, sigma 2 sends root p to root p, but sigma 2 on root q is of minus root q. See, sigma 2 is of order 2, right? Sigma 2 composed with sigma 2 will become identity. And what sigma 3 does, sigma 3 on root p is equal to root p because x3 minus root p. This is your x3. Sigma 3 on root q, where this element goes, it goes to q only, root q. So this is also of order 2, where sigma 4. Okay, so why, how I'm writing sigma i's? Sigma I can be just calculated where the roots of minimal polynomials. This is also discussed in the class if you see class notes. Okay, here, this part one. Galois group restricts to uh, zero set of them, where okay, it was for random f polynomial, but uh, for mu x also it applies same trick, and the number of roots is same as degree of mu x k, and the Galois group, order of Galois group is also degree of extension. So that will also be n. So here that is how we are getting. We are getting four roots of minimal polynomial, and we are getting four roots of sorry, four elements in Galois group. So these are not clearly obvious. Why root p is going to root p only? Why it can go to root q? This is not the case because any polynomial, for example, root p we have x square minus p, x square minus p. Roots of this will go to roots of this. So root p can go to, after applying sigma, root p or or minus root p. So this is important. That is the first point of the theorem, that roots of f, if your f is this in particular, so you cannot go to root q or root minus root q or somewhere else. So this is why I'm writing here. It can go to minus. This is going to minus. So sigma 4 of root q, this is minus of root q. So we are getting this force fit. Now we'll draw the lattice for it, where G fixes all of you here, and sigma 1, which is trivial subgroup, it fixes every element of F. So we will get three subgroups here. Identity, and what corresponds to what fixes root P. Only sigma 2, right? Other than an identity. What fixes root Q other than identity? It's sigma 3. What fixes root PQ? It is sigma 4. fixes root PQ, right? Not P root into root Q because x into y is same as minus x into minus y. That is why root PQ is fixed. Root PQ is same as root P in and which is also same as minus root P into minus root Q. So that is why sigma 4 fixes root PQ. Okay, so this is the latest diagram I have drawn it here, which also applies for uh, in particular 2 and 3. This is all the solutions for 7.2. We'll see next question. We have over 25 minutes. Hello. This question is long, so that it's not going to previous space. Anyway, we'll see here. This is already solved in the hint, but we'll look into it. We'll have a glance into it so that we will finish it early. Well, P a field, GP arbitrary subgroup of Hilbert group. Okay, this is automorphism of Hell. Arbitrary is subgroup of automorphisms of Hell. We don't know which algebra homomorphism. Algebra homomorphism of one. It is not clear. So field automorphisms related. Then we'll take fixed field. This is simply elements of well which are fixed by elements of G. So well, now it is clear. So we have to show that L over fixed G, fixed L is order of G. And when degree of extension is equal to Galois group, automorphism group of K algebras of L is same as degree of extension, it becomes Galois extension. So in particular, if G is finite, this extension, finite field extension is never achieved because degree of extension over here is same as order of G. Order of G means XGL is what? Now the automorphism of L becomes K algebra automorphism of L, where K is this. Okay, that is what uh, we have to understood here. We have to understand this. So we have to one side is clearly very much clear. This is from Pindy kind. The degree of extension is less than or equal to order of L over. Means automorphism of L over K. K is this one. Note it. So other side we have to show it. So we assume that G is finite. Because when G is infinite, this extension, this field extension is also infinite. Uh, I don't know how to show this, but anyway, we, as it is given here, G is infinite, we will assume this. G is finite with sigma 1, sigma 2, sigma n, and order of G is hence n. We'll take n plus 1 elements inside L. Okay, we'll show that it is linearly independent. Sorry, dependent. Dependent, just so that these are random elements of L. So if this set is LD, if x1 xn plus 1 is LD, it's linearly dependent, this will imply dimension, which is L over K, this dimension is less than or strictly less than n plus 1, which is same as saying that it's less than or equal to n. Okay. N is equal to order of G. So this is what we have to show. One side is clear from Artin, sorry, Vedic and Artin theorem. Here, and we have to show this. So we'll show that this set is LD. How will show? We form a basis applying sigma 1 to sigma n in every element here, and we'll get m, sorry, n cross n plus, so n cross n plus 1 matrix, n rows and n plus 1 columns. And if you apply a sigma here, sigma onto this matrix, sigma is any automorphism of G, what will happen? Because everywhere in all columns, rows will be permuted, right? If sigma into sigma 1 becomes, let's say, sigma 2, then it becomes on whole row, right? Sigma 2 becomes first row this way. So rows are permuted. So I hope you understand this. Any linear combination, if there is between these columns, see, number of these are, if you see column vectors, they are column vectors in n-dimensional vector space of L, Ln, Ln. And how many columns are there? N plus 1. So they are linearly independent over L. If they are linearly independent, sorry, linearly dependent over L. Linearly dependent. So there is some linear combination between them. Okay. That linear combination is still valid after applying sigma. Because all the row are permuting. Nothing else is happening. So if there was some linear combination like this, we get linear combination like this after applying sigma. But inside G, multiplication by an element G is an automorphism. So what actually is happening? Actual row, sorry, actual column is just permuting its rows. So this is written here. Same kind of equation is still holds, where this A1, let me write prime here because rows are permuted. So by uniqueness of coefficients, okay. Initially, these coefficients was, yeah, these coefficients remain same. Only rows are getting permuted in the relation, but if you permute them again, these are again y1, this is again yr. So nothing has been changed in the coefficients. Okay, that is what you have to understood. You have to understand here, and then uh, this in this dependence relation is implying that this coefficient, these constants are same. Hence, every sigma fixes this, and y1, y2, yr belongs to things here. So, in particular, this set, this is bigger set. Okay. In fact, we had shown that this is LD over K, right? Because K is nothing but K. Constants are from K, and we are getting some relation between these vectors, so they are linearly dependent over K. That is how we can say. Once they are linearly dependent, and these are all elements of x1, x2, xr, elements of L. So degree of L over K, this is less than equal to L. So that is what we had to show. I hope you understand the hint. The hint is only complete solution. Okay. So if you are not clear, you can read it once more. Okay. For 7.5, L over KB finite field extension. J is a subgroup of Galois group, so that J is finite and its order G divides degree of extension L over K. Okay, where L is here, K is somewhere here. So we'll take LG, right? C was complete a whole Galois group, this extension. It is also not clear this is Galois extension. So if it was Galois extension, then LG will have become K equal to K. In this case, it lies in the middle. Okay? Because we are not, but this extension is Galois. Why? You have just seen, right? You have just from L over LG. So this is Galois extension. Now, once L over LG is Galois extension, and it lies in the middle of this. So, particularly L over K, this can be written degree formula. I'm just writing degree formula L over LG, LG over K. Okay, let me note that LG is nothing but fixed subfield of L x by D. This is the notation. If you don't read it properly. Okay, now from here we get that this part from 7.4 implies L over K, which is same as L over LG, which is Galois extension. Let me show you L over LG. This is what? This is written L over LG. This is equal to order of. That is what I'm using here. So this is order of G into LG over K. But this will imply that order of G divides L over K. This extension. Degree of this. This is what we had to. So first part, or equal to holds if and only if L over K is Galois. If order of C is equal to L over K, then from this relation, which is, let me say, star, star implies that LG equal to K. LG, this degree extension is 1, in particular LG is equal to K, means fixed field by G is just K, and hence this implies odd automorphism of L over K, this is G, and this is Galois group is G. When Galois group is order of Galois group is same as degree of extension, this implies Galois extension. This implies Galois L over K, order of this is same as L over K, degree extension. This implies that L over K is Galois extension. And what else we have to show? Galois group of L over K G. This is shown here. So this is, and we have shown it. Now on the other side, that is clear, right? If your extension is Galois and Galois group is G, if L over K is Galois, Galois extension by definition, and G is equal to what? L over K, that is Galois group, then Galois extension by definition of Galois extension by definition, we have order of G same as degree of L over K. Okay, so this was also easy exercise. This was this was target. Obviously, we had done 7.5. Let's see next question. We don't have much time, but we'll look into it. How much we can. We have 2 more minutes. I belongs to Kx, which is function, rational function over K. So that field extension Kx over K5 is finite. Or Kx over K5 is degree of phi, where degree of phi is defined as maximum of degree of f and degree of c, where phi is represented by f by j, and z and f are relatively prime. This is done in exercise 5. I have solved this. Hint is already given. So it is exercise 5 point something. I don't remember. Let me write. Fifth week. These two parts. Fifth week live channel. I have discussed it. Discussed it. You can look 5.3 or 5.4. I don't remember. These two questions have been discussed. Okay. Uh, yeah, this part is if you have understood, kx over k5 over k. This is finite degree extension, finite degree extension, and its degree is degree of phi. Means maximum of degree of phi is defined like that. Okay, maximum degree of f and max between maximum between degree of and degree of where phi is represented by fy. This is finite degree extension. What you expect, and there is no extra. So hint in the hint it is wrong hint. There is a, you have to take care a little bit. Here it should be e minus k. Okay, e minus k. Then e will be somewhere here in between. Okay, and because this kx over k5 is finite, e over kx over e is also finite, and then it is clear kx over is. We have to take this phi from E, but not in K. So K5 should be subfield of E. That is what E lies in the middle. Figure is finite, this figure extension is finite, so E is also finite. Kx over E is finite extension. That is what is okay. Okay. For C part, phi be f by g, and Kx, which is not constant, phi is some non-constant function. F and C are co-prime. So that map, evaluation map at phi, x goes to phi, scale algebra homomorphism, or it is a scale algebra orthomorphism if degree is 1. This is clear, right? That it is scale algebra homomorphism where constant goes. Constant evaluated at phi will be same constant because there is no appearance of x variable. So where to put phi? So constant evaluated at phi, that is anyway phi. So constants are anyway fixed. So this map, evaluation map, is K-algebra homomorphism because this map fixes the constant, fixes the elements of K. That is clear. Okay. So we have to show K-algebra automorphism if and only if degree of phi is 1. Okay, this part is nice. We have seen in the part A that Kx over K5, this is of degree extension is just degree of phi. If degree of phi is 1, right? What is image anyway? What is image? Let's say this map is phi. Psi of kx is nothing but because of evaluation map, right? It's it is nothing but k phi. So image is k phi, and any field homomorphic, If it's field or homomorphism, K-algebra homomorphism, then it is automorphism. Any field homomorphism is anyway injective, right? So this psi is injective map. Psi is injective map. Now let me write here. This is about part C. It's psi from this is psi kx to kx, where f by g goes to f fx by g f of phi g of phi. Psi is injective. This is always true for field homomorphism. Uh, if we show this is subjective, then it is clear, right? Psi is isomorphism. The question is asking when psi is isomorphism, is automorphism, if and only if degree of phi is 1. When degree of phi is not 1, then k phi, which is also psi of kx, this is subset of proper subset of kx, and this extension is degree phi extension of um, okay, which is kx over k phi. So it is not surjective. This implies psi is not surjective. When degree of phi is just 1, then k phi, which is image of this kx, inside kx, this extension is degree 1 extension. Degree 1 extension. This implies psi of kx is same as kx. Hence, psi is surjective. This was only needed proof. Everything else is clear. This is algebra automorphisms. Okay. I hope you understand that part. So we have done C part. So similar C parts. This hint is given. So any automorphism of Kx over K is of this form, right? Ax plus B divided by Cx plus D, where A, B, C, D are arbitrary choice, but Ex plus D is non-zero. And yeah, of course, degree maximum degree should be 1. So if one is constant, let's say numerator or denominator, then the other one should be of degree 1 polynomial, so that A or C correspondingly should be non-zero. Okay. Now, because F and G both are chosen such that they are co-prime, Ax plus B, so it is not multiple of Cx plus B. This implies that AB and CD, they are linearly independent. Okay, because the first row is not multiple of second. Okay, over K. So A, B, C, D, this matrix, because both rows are independent, one is not multiple of other, I'm just saying, their determinant will be non-zero. So they belongs to GL2K. That is invertible matrices 2 cross 2 over K. Now any automorphism of AX over K will go to, we have a natural choice of this matrix ABCD, and we'll take the quotient with K star. Hmm. Okay, because of what? I don't know why we are taking modulo K star. Any automorphism will be of this form, so you will get ABCD will be invertible matrix. If two matrices are multiple of each other, scalar multiple of each other, will they give same automorphism of Kx? I don't think so. For example, inside AF, if we take x goes to 2x, okay, and x goes to x goes to x is identity homomorphism of x. But x goes to 2x, it's not, it's not identity. But I think that is clear. It may explanation why we are taking quotient from K star. Okay, I'm leaving that as exercise. You just check it and come to next class. Yes. Okay, so we have more in this part. We are 10 minutes late, but we'll quickly go through it. If K is infinite and fixed subfield of Kx by this group, Galois group, is K only. So Galois group is generated by these three kind of automorphisms. It could be of form AX, X goes to X, or X goes to X plus B, or X goes to 1 by X, three kind of automorphism. And uh, any rational function which is fixed by this kind. Uh, no rational function is fixed by these things. If f is a rational function, f is not fixed by this, okay, or this, or this. Only constants are fixed. Let's say, for example, a polynomial. Where a polynomial goes, fx becomes fax for every a. This is an automorphism for every a, right? Non-zero a. So if x is a root, all multiples of x is a root of f. No, no. Only finitely many roots can occur. K is infinite. So This is true for infinitely many for A belonging to K star, and K star is infinite. If F is fixed, if F is belong to fixed K by Galois, then this will hold, and this implies F will be zero polynomial only, right? That is why. So if F is constant zero or constant, so only constants. So fixed field will be just K. This is also clear. I hope you understood this. What about next part? Some Kx over K5. What is degree? This degree of extension, degree of 5, right? And I was just recalling this, which was not needed. But Kx over fix. This is Galois extension. And what is degree of extension? Is order of G, whatever G is here. So order of G, you can just calculate will be this, which is just order of PGL, PGL2 of FQ. Okay, this is what here it is. You can calculate it. You can ask me later if you wish. Similar thing is this. We are collecting translation maps in the subgroup of Galois group. Moreover, this is isomorphism of group. This is also clear. You, it needs a verification, but it is clear. True translation will give extra translation means first translate by A, then B. So it will be translated by A plus B. So A plus is isomorphic to this translation subgroup. If K is infinite, then we have to show that no rational function is which is constant, which is not constant, it's fixed. Only constants are fixed. We have to show. If your rational function is, let's say, f by g, so sigma will apply to f, it will give f, sigma applies to f, g, it will give g. So what I'm saying is only polynomial which is fixed by sigma, fixed by translation, will be constant. I hope you see it. If f is a polynomial, let's say, and translate by a, fx will go to fx plus a. If it is again fx, what it means is that if x is a root, x plus a is also a root. And it is true for all translation because it should be fixed by all the translation. So it has inserts many roots. F should be 0. Okay. Or there is no translation happening at all. So it is a constant or 0. Okay. In this case, only 0. Uh, yeah, it can be constant also. Because if it is constant, and if you replace x by ax, because there is no x involved, so no need replacement x by ax. So it is constant for it. That is it. So same trick e as e. Now what about g part? Assume characteristic k0 is non-zero element. S tau be subgroup generated by a translation, a single translation, X translation. So that G is infinite cyclic. Because A is non-zero, this translation is non-trivial. So one non-trivial element, and it has because characteristic is zero. That is also important. This field is infinite, and A, A plus A is 2A, 3A, 4A, 5A. All of them is non-zero because characteristic is zero. You will not get any n such that n into A is equal to zero. So uh, all these are non-trivial elements, right? And it's non-zero. Let me write here. N into A is not equal to zero for every n because characteristic is zero. Okay, that is why these elements tau A, tau 2A, tau 3A, they are not trivial. They are one-to-one correspondence with elements of Z. Okay. Tau 2 goes to tau 2A goes to 2, tau 3A goes to 3, like that. So it is Z, isomorphic to Z. Infinite cyclic is clear. Determine if we have gone 20 minutes late, but we have not discussed all of these things. But hint is given. If you see hints, you will find the solution. Okay, use them according to your choice. If you don't want to use hints, you can solve them by your own way. Determine the fixed field Kx and what is degree of extension. Let me write it is K, and this extension will be infinite. Okay, how I'm writing it? Same trick. Which polynomial is fixed by single trans? Because tau, because it is infinite cyclic, this is just isomorphic to Z. And for infinitely many translations, single polynomial cannot be having infinitely many roots, same trick as E or as F. So only constants F can be constant. That's all. Okay, so I don't even second it possible. Uh, once G is infinite, 6G will be any with Q. Okay, so that's all. So this degree of extension is also infinite. Same trick. What about this part? 7.10. Sigma and sigma prime. Sigma is sending x to x minus x. Y x is y. Okay. Sigma prime is sending both x to minus x, y to minus y. Multiplication by minus 1. We have to show that x, 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 and y, g is r x square. Any polynomial fxy, apply sigma to it, where x appears, sigma will go to every element. This becomes equal sigma x, sigma y, but sigma x becomes minus x, so this becomes f minus x, and sigma y is just y. So what you see here, you just want to check which one is fixed. Fxy. Fxy, you want to find f such that fixed by sigma, right? So that is why I'm writing here. But when it is, so this implies only even power of x survives. This implies only even power of x appears in f. Appears in f. Otherwise there will be problem, right? This implies f x y belongs to r x squared. No x appears. There's no odd term appears. So this is something f belongs here. And this is already clear. This is anyway belongs to fixed phi sigma of L. Okay, so here we have to f belong to fixed sigma, and we have found f belongs to Rx squared per y. And this is clear. If x square y only appears there, then it is fixed. Okay, so I hope you understood this. It's almost 2.5 hours. I'm letting end here. If you don't understand, then you can comment into this video, and most probably I will reply some of that when I will be finished.